let's jump right in. So to kick off this presentation, I want to begin by telling you a story that takes place in the year 1993. Now, the year 1993 is a pivotal year in computing history because it marks the beginning of what is known as the browser wars. Now, just 3 years prior, Tim Berners-Lee at CERN had just invented ARPANET, thereby birthing what would later be known as the Internet. And in this year, the year 1993, we have the creation of 3 major browsers: the Lynx browser, the Arena browser, and the Mosaic browser, each vying to become the first viable user interface to the World Wide Web, each bringing with them their own opinions on what a browser should be and how the markup language of the web should be, and each rapidly innovating, eager to bring about the new wave of the internet. Lynx browser was the first to the scene. It brought with it the concept of HTML, followed by the Arena browser, which brought the concept of a GUI for the web and also introduced the concept of the image tag. And last but not least, the Mosaic browser brought with it a whole slew of new tags, such as form tag, nested lists, etc. And also not so desirable tags, such as the blink tag and the marquee tags. And so 1993 was a period of dizzying innovation in the browser sphere. All these browsers had wonderful ideas on where the specs should go for HTML, and sometimes these ideas were at conflict. So in the year 1994, all the major engineers and academics behind the browsers decided to convene in Geneva for what was known as the W3C, or the World Wide Web Consortium. And here's a picture of that very first meeting. And the W3C essentially hashed out what the spec for HTML and the web should be. And because of what W3C and what they did, we now have a standardized spec for HTML, JavaScript, and CSS, and we can pretty much have a very consistent experience across all the major browsers. And one would think that the introduction of the W3C would introduce extra overhead to the various browsers, but it really hasn't. Browsers are still innovating at a rapid pace. Here we have a picture of the web GPU experiment that Firefox is running on Firefox Nightly. Here's an image of HTML portal element, which is an experiment that Chrome is running on Chrome Canary. And what W3C brought to the table is process and visibility into its innovation cycle. And so you're able to track how web GPU is progressing via their website and how Portal is progressing. It's very cool. And the reason why I bring up the story about the browser wars and the forming of the W3C is because it's a story about an ecosystem. And ecosystems share a very fundamental concept called ecosystem lifecycle. Every ecosystem starts from some sort of solid foundation. It will then go through a period of rapid growth. And then finally, consensus and best practices will emerge in that ecosystem. And if it's so called for, standards will emerge as well. And it turns out that a React Codebase is also an ecosystem and a subject of this talk. A React Codebase will grow over time, and the team members that write in that React Codebase will grow over time. And these team members will introduce new best practices, new concepts, new packages, entire new ways of thinking into a React Codebase. At some point, we'll want to start tracking these ideas and how they evolve. We'll want to identify trends, emerging best practices, and where we need to improve. Just as the W3C did for the browser sphere back in 1994. And once we understand these trends, we can begin to promote them and reinforce them, and if it's so called for, introduce standards and guidelines. And so the purpose of this talk is to get you to a point where you could be the W3C for your own React Codebase and learn some strategies on how to manage and guide the growth of your codebase. And the process by which we'll be doing so is this 3-step process. We'll first go over how you can ask quantifiable questions about the health of your React Codebase. how you can answer those questions using static analysis, and finally, how you can crystallize those best practices by turning your analysis queries into, say, lint rules or into code mods. And well, we won't be going over. So this is Reactathon after all, and we will be focusing prominently on React. And anything outside the scope of React, it won't be covered. So bundle stats, code styling, CI/CD, all these things are important, but you can get information on these elsewhere. And a little bit about me before we begin. My name is Bryan. My alias is for me Dirac, sometimes just Dirac. And I work on the front-end infra team at Flexport, and I've been working here for about the last 2 years. Why you should listen to this talk is Flexport has one of the largest and oldest React codebases. We adopted React 5 months after it came out, and we're pretty much a React monolith on the front end. I also contribute to React and React-like projects like DocGen. All right, let's begin. So, Codebase Health. Before we can begin quantifying anything, it's important that we ask ourselves where a codebase is in its history and also where it's going. What is the state of our codebase today? When we think about these questions, it's important that we pose them in terms of codebase health. How stable, how readable, how maintainable is our codebase? And by asking these questions, we can begin to understand and get a better feel for what's working, what isn't working, what needs improvement, and how we can improve those things that need improvement. And so in this slide, since this is Reactathon, I have some examples of questions that you can formulate around the health and state of your React codebase. So let's just go over them. Are teams creating too many redundant components? Is our design system library over generic or not generic enough? Are engineers still using a legacy approach to a certain system, say CSS styling? And if so, why? Are we adhering to accessibility standards? And should this particular category of component be generalized into a shared component? So all these are questions, subjective questions that you can ask about your React codebase. And in the next slide, we'll go over an exercise on turning one of these questions into an objective question with objective answers. So let's focus on one of those questions. Is our design system library overly generic or not generic enough? And to paint some context, let's say your company has an internal design system team, and that team wants to understand the adoption of their component to library. I always urge to probe deeper. Go talk to that team, figure out exactly what they want, and figure out metrics based on your conversations with them. So let's say you go talk to that team and you figure out that they're working on a slew of form UI components, and they want to understand their adoption rate and what they need to do in order to drive adoption. Well, now we have something to work with. We can formulate a question off that. What percentage of forms in our code base use the form UI components from our design system? And of the forms that don't, let's just list them. That way the team can go talk to those form code owners and figure out what they need to do to drive adoption. And that gives us some quantifiable data that we can track. One, the adoption rate of form UI components, and two, a list of forms that are not using form UI components. And though these queries seem to be nebulous, it turns out that we can answer them, though very loosely, with static analysis. And the tools of choice that we'll be using are AST Explorer and JS CodeShift. AST Explorer is a tool that will help us mock and test out our static analysis queries, and JS CodeShift is a library that we'll be using for actually writing these queries. All right, so this is AST Explorer. AST Explorer is a tool we'll be using to explore running static analysis queries with. It consists of 4 panels. The top left panel is some source code we'll be testing against. Here we have an example form called myForm, which imports some form UI components, renders some stuff, and then it returns the form. On the right-hand side, we have a tree representation of our source code. So if I were to, for instance, highlight this import declaration, On the left-hand panel, it highlights the stringful import declaration. If I were to highlight this block statement, it highlights the block statement to the form. It's essentially a true representation of our source code. And then on the bottom left-hand corner, we have our transformer. So a transformer for JS CodeShift takes some source code and outputs resulting source code. So here it's parsing our source code, looking for any identifier, and then reversing the text of that identifier. And you can see that in the output on the bottom right panel. All the identifiers are reversed. For the sake of this presentation, we're not interested in transformation, so we can delete this, and it'll default to just returning our source code as is. Going back to our formulated question statement, what percentage of forms used to form UI components? We can now break this question down into two distinct steps. Step 1, get a list of the form components in our codebase, and in step 2, from that list, determine which forms contain any form UI components. And the way we'll be doing so is by looking at the components' import statements. So for step 1, it turns out for the theoretical codebase that we're working on, doing this is pretty simple. All forms have the convention of ending in form.jsx, so we can simply walk through our project directory and match for any component file that matches that regex. For step 2, in order to determine whether a form contains form UI components, we'll do what I described earlier. Check the form's import statements. And the way we'll be doing so is via JS CodeShift. So the first thing I'm going to do is I'm going to copy over this list of form UI component import paths into this file. This is a list of all the known form UI components in the import paths. And our strategy is going to be first find all the import declarations in this file, and then check if any reference the above import paths. And so it turns out with JS CodeShift, this is actually quite straightforward. We simply call tree.find JS CodeShift.import declaration, and we care about this import path, so we call .find again. This import path is a literal, so we call find.literal. And if we run for each on each of these literals and console log each of them, or rather their value, let's open up our console, we can see that we are indeed hitting these import paths. This is what a full implementation ends up looking like. Now, for those of you who want to read this code and dig in, don't you worry, at the end of this presentation, there's going to be a link to a GitHub gist with the full implementation that you can read, play around with, and do it as you please. So I hope this section gave you a quick taste of what it's like to write a stack analysis query, and I hope it didn't go by too fast. The final section, crystallizing best practices. I'm going to throw you a new scenario. Say your company is doubling down on internationalization, and through analysis we found that we really like I18N. We don't want to have any free-floating text literals in our JSX. Everything must be passed through I18N for internationalization. And our company wants us to enforce this as a standard. So there are two ways we could go about this. The first way is we can introduce an ESLint rule. Here we've introduced a new rule called no string literals, and it'll create a violation whenever it finds a string literal free floating in your JSX. This is extra work for your engineers because it means that they'll need to dig into the code and remove these violations and fix them themselves. And the other approach is we can write a code mod. Now, the query we wrote was in JS CodeShift, and the purpose of JS CodeShift is for writing code mods. And what a code mod is essentially a transformation of code. You go from one type of code to another type of code. And here we've transformed all these free-floating text rules to be passed through I18N. Now, using code mod isn't always possible. For instance, there might be too many edge cases or a lot of complexity. But in general, you should always favor writing code mod. And if you can't, definitely go for an ESLint rule. So yeah, those are two ideas on how you can crystallize best practices. And that's it for my presentation. Reach out if you have any questions. I'm going to be at the topic tables later today, so you can talk to me there or reach out earlier. Doesn't matter. And as promised, there are links to the code samples. That's all. Have a good React Con, everybody. Thank you for listening to my talk.